Hello and welcome. In this video, continuing on from the last one about BLAST, I'll be talking about how you evaluate BLAST hits and how many high-scoring alignments can potentially be due to randomness. So the values are more or less significant depending on the query size, right? Because if we use a really small query like GATC, for example, and search the entire human genome for it, of course, we're going to find a lot of hits for that simply due to randomness and the increasing probability of running into something when it's really small. The significance is also dependent on the percent of the query that the alignment covers. So if I have a large sequence and I search a huge database, and maybe a small portion of it, just 1% of it has a really good alignment somehow, this might not necessarily mean anything. And then finally, the percent identity between the query and the database sequence. We would be looking for mismatches, and the more there are, the less significant that hit would be. And some considerations that impact the result are things like the number of entries and the length of the entries in the database. The bigger the database, the more likely we are to find random sequences because there are more sequences available in the first place. And then also the length of the query. So the smaller it is, and I said this just now, the smaller it is, the more likely we are to find a match. And then this brings us to something called the e-value, which is a test for statistical significance. And we're going to use this e-value to determine whether we should trust our hits or not. Alignment scores and sequence length. So if we do a lot of experiments of a particular query aligned with random sequences, and we are to just keep track of the highest score every time, and we ask how frequently do we get certain scores, we would see that the highest score tends to follow what's called an extreme value distribution, a probability distribution, where the majority of results would be clustered in this kind of peak here, this mountain in the distribution. So you can think of this as a frequency or a probability. And the extreme value distribution has this very long tail of unlikely but non-zero probability of encountering much higher scores. So somewhere out here, there is a score of 100 that can occur due to randomness for these particular parameters. And what are these parameters? So these are the parameters that determine the shape and spread and location of this particular curve. So there's an equation that generates it. And one of the parameters, for instance, is the alignment score that you're looking for. And another is the query length and the database length. And then we have some other constants that are related to the substitution matrix. And there's something called the Carlin-Altschul equation. And this is what gives us our e-value. So what is the e-value? It is the expected number of sequences that we will get above a particular score x. And you calculate it from this. And it turns out the proof and the derivation of this equation is very complex, but this equation itself is very easy to use. Basically, it's just a matter of plugging in these numbers, and they are things like the query length, m here, and n, the database sequence length. And if we said that we have an e-value of 10, then this would be equivalent to saying that we expect to find 10 hits due to random sequences, due to unrelated sequences. 10 hits due to randomness. So obviously, the lower the e-value, the more significant the alignment. And then a slightly rearranged version of the cumulative probability distribution gives us something called the p-value. And this is similar but not exactly the same as the e-value. What the p-value is it's the probability of obtaining at least one random alignment of the score S greater than our score X. So again, the lower this number, the more significant the alignment score we got is. And it's calculated simply with 1 minus the exponential of minus e, with e being the e-value. And you can think of it this way. It's like asking, what is above, a certain point. If we pick a score x here, then how much of this cumulative distribution is left over out here? And we can see an example here. If we had a length of m equals 100 bases and database length of 100,000 bases, parameters k and lambda here, and we pick a score of 86, then we get a p-value of 1.1 times 10 to the minus fifth. So there's a probability of obtaining at least one random alignment of score S greater than 86. That is 1.1 times 10 to the minus fifth. So a very low probability. And some rules of thumb for these numbers are that for proteins, usually if your number is less than 10 to the minus 6, then you're almost certainly looking at homologs, related sequences. But unless the e-value is extremely low, you always want to manually go in and look at the alignments themselves. And you can be fooled easily. So sequence identity can be low. So for example, 15%, but you can have a e-value that is 10 to the minus 30. And this just depends on the attributes of the database and the query sequence that you're using. Yeah, so don't stare blindly at one statistic. Try to look at everything. Large proteins with a high level of similarity often have insane e-values like 10 to the minus 50, extremely low. Nucleotides, so fewer bases, right? Just GATC. These tend to have worse e-values, and you use you use lower cutoffs. For example, 10 to the minus 10. And multiple databases are available online for using BLAST at NCBI. So there's nucleotide BLAST, protein BLAST, and a good procedure to follow is to start out with a generic database. And if you happen to get no hits, then you would maybe refine your, choose another database, choose a specialized one. And it's important to note that BLAST should be treated kind of experimentally. So BLAST searches depend on things like the database, and the database is constantly changing. It's being updated, and the results are non-deterministic, so you can get multiple answers potentially for the same input. So you should take note of the parameters of your search. Take note of the date, for example, and the cutoffs you use, and other parameters. And you should perform controls, especially when the percentage of sequence identity is low. Only believe your result when controls play out as you expect them to. And view the results graphically because we're much better at visually interpreting data. And study the alignments themselves between the query and the hit. This can often give you insight. And then finally, be skeptical of unconfirmed proteins. There's a lot of types of entries in these databases, and the quality of them is not all the same. So these are some references. Here we have Altschul, as in the Carlin-Altschul equation. So check those out. Yeah, to summarize, it's the most common program for sequence searching. E-values, the lower the better. Multiple methods, nucleotide, protein. It's available online. You can also run it locally. And you should choose a search database based on the type of sequences that you want. And that's all for this lecture. So I'll see you in the next one.